Effect of a velocity-dependent scattering cross-section. Suppose that the molecules of a gas interact with each other through a radial force F, which depends on the intermolecular separation R according to F is equal to C times R to the power minus S, where S is some positive integer and C is a constant. Use arguments of dimensional analysis to show how the total scattering cross-section sigma of the molecules depends on their relative speed v. Assume a classical calculation so that sigma can only depend on v, the molecular mass m, and the force constant c. Okay, the total scattering cross-section sigma dimension-wise is the dimension of pi d squared, which is length squared. Now, the dimension of the force F, the force that depends on the intermolecular separation, is mass times acceleration, which is mass m length L divided by time square. So this is coming from Newton's second law. And that, according to this force that develops, radial force that develops between the gas molecules, is the dimension of the coefficient C multiplied by the dimension of the radial distance r to the power minus s. So this is basically the dimension of C divided by the length to the power s. So it's the dimension of r to the power minus s. So we can see that the dimension of this coefficient C is equal to the dimension of the force ml over t squared multiplied with L to the power S. So we obtain m L to the power S plus 1 divided by t squared as the dimension of this coefficient. Now we are given that the total scattering cross-section can only depend on V, M, and C. So therefore, the dimension of the total scattering cross-section must be equal to dimension of C to some power alpha, dimension of the relative speed V to some power beta, and dimension of mass to some power gamma. Okay, now what is the dimension of sigma? It is L squared. So we can see that L squared must be equal to dimension of C, which we have found to be m L to the power S plus 1 divided by t squared to the power alpha. Then dimension of the relative speed v, the speed dimension is length divided by time, to some power beta, and mass to some power gamma. Therefore, we obtain mass m to the power alpha plus gamma, length to the power alpha s plus alpha plus beta, divided by temperature T to the power 2 alpha plus beta. All right. So this must be equal to L squared. So we can basically find what these coefficients should be so that this is equal to L squared. So first thing we notice is that 2 alpha plus beta should be equal to 0. This should be T to 0 because there is no temperature here. So the first equation is 2 alpha plus beta is equal to 0, which gives us beta is equal to minus 2 alpha. And then for alpha plus gamma, there is no m dependence here, so alpha plus gamma should be 0 as well. So we find alpha plus gamma is equal to 0, gamma is equal to minus alpha. And for the power of L, alpha s plus beta should be equal to 2. So we have alpha s plus alpha plus beta, where beta is minus 2 alpha, so let's just substitute that here. Minus 2 alpha should be equal to 2. So this gives us alpha s minus alpha is equal to 2. In other words, alpha is equal to 2 divided by s minus 1. Now with that, we can substitute for beta. Beta is equal to minus 2 alpha. So it is minus 4 divided by s minus 1. And for gamma, which is equal to minus alpha, we have 2 divided by not s minus 1, but 1 minus s because of the minus sign. So we see that the total scattering cross-section depends on C, V, and M in the following manner. It is C to the power alpha, which is 2 over s minus 1, V to the power beta, which is 4 over 1 minus s, and M to the power gamma, which is 2 over 1 minus s. So here we have found beta is equal to 4 over 1 minus s because of the minus sign. Or we can write the total scattering cross-section is C divided by mv squared to the power 2 over s minus 1. So let's check. It should be C to the power 2 over s minus 1, V to the power 4 over s minus 1 with a minus sign, M to the power 2 over s minus 1 with a minus sign becomes 2 over 1 minus s. So that's the answer to part A. How does the coefficient of viscosity of this gas depend on the absolute temperature T? The coefficient of viscosity, eta, is equal to 1 over 3 n V bar ml, which is, as we have shown many times, 1 over square root 6 square root of mkt divided by the total scattering cross-section sigma. And as you can see now, the coefficient of viscosity varies as T to the 1/2 divided by sigma, and that's because we have V bar is proportional to square root of temperature. And now we have found that the coefficient of viscosity varies as T to the power 1/2 divided by sigma, but for sigma here we have C over mv square, and for mv square we can say that this is proportional to T using the equipartition theorem. So basically for mv square, if we substitute T, this is going to be T to the power 2 over 1 minus s. So this mv square has temperature dependence T due to the equipartition theorem. 1/2 mv square is 1 over 2 kt, the equipartition theorem. So you can see that v square is proportional to t. So we can write for the coefficient of viscosity a temperature dependence t to the 1/2 plus 2 over s minus 1. So this gives us a temperature dependence as t to the power s minus 1 plus 4, which is s plus 3 divided by 2 times s minus 1. Okay, so we have a velocity-dependent total scattering cross-section. By doing dimensional analysis, assuming a radial force between the molecules c times r to the minus s, we want to find the total scattering cross-section dependence on v, the relative speed, the molecular mass m, and force constant c. Using dimensional analysis, the dimension of the total scattering cross-section is length square. Dimension of the force is mass times acceleration ml over t square, which is dimension of c divided by l to the power s. So we obtain dimension of c m L over t square multiplied by L to the power s, ml to s plus 1 over t square. And this sigma is given to be dependent on c, v, the relative speed, and the mass m. So c to the power alpha, so m over l to m times l to the s plus 1 over t squared to the power alpha. V to the power beta, the dimension of the speed is length divided by time to the power beta, and dimension of m, mass, m to the power gamma. This must be equal to dimension of sigma, which is L squared. So we see that 2 alpha plus beta should be 0, alpha plus gamma should be 0, alpha s plus beta should be 2. So this is basically m to the 0 divided by t to the 0. All right, so solving these equations, we find alpha is alpha s plus alpha plus beta, alpha s plus alpha plus beta is equal to 2. But beta we have found from this equation, 2 alpha plus beta equals 0 to be minus 2 alpha. So if we substitute that here, we obtain alpha s minus alpha is 2, or alpha is 2 over s minus 1. Beta is minus 4 over s minus 1. Gamma is minus 2 over s minus 1. If you operate the minus sign at the bottom, we obtain 1 minus s. So sigma is c to the power alpha, which is c to the power 2 over s minus 1, v to the power beta, v to the 4 over 1 minus s, m to the power gamma, m to the 2 over 1 minus s. So in other words, this is c over m v squared to the power 2 over s minus 1. Now, the coefficient of viscosity dependence on temperature can be seen using this sigma value. We have already square root of t on top due to the v bar, the mean speed of the molecules. Now we have this total scattering cross-section that depends on the velocity. Now the velocity mv square average value is proportional to t. So this is proportional to t. So we can see that v square bar is proportional to t. So if you substitute that here, this is from the equipartition theorem, we obtain t to the power 1/2 dependence from the square root mkt, and from sigma we obtain v to the power mv square, we substitute t here, so it's t to the power 2 over 1 minus s, that's for sigma, because it's mv square is, if mv square is proportional to t, then that means sigma is proportional to t to the power 2 over 1 minus s. So that's what we substitute here. And if we take this ratio, we obtain t to the power s plus 3 divided by 2 times s minus 1.